Hello everyone, I'm Baotong Tian from University of Rochester. Today, I'm going to present our work, Conan, a chunkwise online network for zero-shot adaptive voice conversion. This is a joint work with Zhang from Zhejiang University and my advisor, Zhiyao Duan. So we are dealing with the problem of streaming voice conversion, and it actually has a visual grounding coming from a very popular Japanese anime called Detective Conan. So Conan is a brilliant detective, but he has a problem. He cannot reveal his true identity. So every time he tries to solve a crime, he would use his red tie, which is a voice-changing bow tie. He would normally say, "Shinjitsu wa itsumo hitotsu," which means that there is always only one truth. And then he will start saying what he inferred from the crime scene. So streaming voice conversion also has real-world applications like immersive gaming, content creation, digital entertainment, live streaming, and also virtual meetings. So for voice conversion, by definition, it aims to transform the speaker identity of a source utterance while preserving its linguistic content. So normally how we deal with this problem, we have a content branch. So we try to extract content-related information from the source speech. And then we have a speaker branch where we try to get a speaker embedding or speaker information, which normally a global embedding from some kind of decoder, encoder from reference speech. And we concatenate or aggregate the information together. We pass that through a decoder to get the generated speech. So that's how we normally do it. So to emphasize source speech, we need to keep the content, and reference speech, we need to keep the speaker timbre. So we're moving from VC to zero-shot streaming VC. So is it harder? Yes. So zero shots means we're doing on-scene speaker transformation without any speaker-specific fine-tuning. So how do you model a speaker timbre or style without seeing the speaker during training? So it's definitely harder. For streaming, algorithmically, we're doing chunk by chunk processing. So we can see the whole audio is divided into chunks with a predefined chunk size. So if we process that chunk by chunk, it will have a problem of discontinuity. So like the content, it will be discontinuity. And also the quality may be low because of the artifacts generated, also because of the discontinuity. So these are the three difficulties we're facing, and we have three corresponding architectural design to help address the problem. So first one, the speaker style modeling, we're introducing a new branch called adaptive style encoder. And for the content discontinuity part, we improve the content branch to introduce the stream content extractor to better extract information in a streaming fashion. And for the low audio quality problem, we improve our synthesis module to introduce the causal shuffle vocoder. It's also specially designed as a causal model for streaming scenarios. Okay, time to see our overall architecture. With our previous knowledge about voice conversion, how we deal with it, it's not that hard to understand. So let's walk step by step. First, take a look at the green part. We're doing the chunkwise source speech processing, the content branch. So we're doing a chunkwise extraction of content to obtain the content embeddings. The orange part, speaker embedding. We use timbre encoder to extract information from the reference utterance. And our contribution one, the adaptive style encoder, which is the style branch, still from reference speech, and we feed that to the style encoder to get the style embeddings. Now I have three embeddings. We feed that to the F0 prediction part, which is a causal wavenet architecture, and we get the F0. Okay, now we have four information. We feed all that information to the Mel spectrum decoder, and after our designed causal shuffle vocoder, we get the generated speech. So that's our system of approaching the zero-shot streaming voice conversion problem. Okay, so now let's dive into details. So to improve content discontinuity, we adapt the informer architecture for a streaming Hilbert distillation. So informer is abbreviation for like efficient memory transformer. So it has like transformer attention mechanism, but it's designed for like streaming speech scenarios. And it has cached contextual information from previous chunks so that we can maintain continuity. And it also includes some look ahead for trade-off between latency and accuracy, because the look ahead means that you have limited access to future information that would be beneficial to infer what the content is at the current time step. And how we train this model, we use the distillation method. We are using a streaming architecture to distill the discrete code from the Hilbert model. So Hilbert is a transformer model, and it's a bidirectional, so it has very long attention span, so requires a lot of future information, not very adequate for our task. So we're using the informer architecture for distillation. Okay, back to architecture. Now we introduce the blue part and the yellow part. First one, the adaptive style encoder. So it seems it is simple. So we put the reference smell spectrogram to convolutional blocks, like these normal operations, and we use vector quantization. Here we use clustering vector quantization as some bottleneck to filter out some like content related information. And then we also have the align attention mechanism, which is guided by the content embedding and the timer embedding to select the corresponding style embedding, which is related to the content. And we have the causal shuffle recorder to improve audio quality. So that is how the input is the MEL spectrogram and the output is audio. So normally how we do with like causal convolution is that we use a transposed convolution for upsampling. Here we only use pixel shuffle as upsampling method. So it only manipulates channels and is fully causal. So let's see here for the animation. 3, 2, 1, go. Yeah, so we're only manipulating channels without adding or deleting information. So mathematically, we have a matrix like the RNC is the channel dimension, and the Tn minus one is the time dimension. So um, we're upsampling n times. So we have the n here. So normally, the pixel shuffle is that we're turning the matrix of RNC by Tn minus one to C by Rn times Tn minus one. So yeah, it will more effectively reconstruct audio details because we're not adding or deleting any information. Okay, enough about fuzzy technical details. We talk about inference here. So yeah, streaming. So at the beginning, we need to wait until the input reaches a predefined chunk size plus a look ahead if the informer permits before passing it to the model. And also we employ a sliding window strategy, and we only extract a segment of the current chunk from the model's output. So from this diagram, we can see three parts. The gray part is the past context part. The green part is the current chunk part, and the blue part is the look ahead part. So we feed all these three parts to the Conan model. However, we only care about the blue parts, the green parts, the current chunk parts that we care about. So we only extract the green parts as one component of the output because we're going to concatenate with other chunks by like different passes of the models. Yeah, so that's our inference process. Additional experimental settings, we train a model on libTDS datasets and we include VCGK for evaluation. We have two versions of the model. The main model has 80 millisecond processing chunk, 1 second of past context, and 40 milliseconds of look ahead. The look ahead is only for the informer or the stream content extractor, and the rest of the part is causal. We also have a fast version. We have a 20 millisecond chunk, a smaller one, and 1 second of past context, and no look ahead. So the full model is causal. Here are some results. some numbers. First, let's see the speaker similarity. We get the highest speaker similarity, which means that our timbre encoding and the style encoding it works. Yeah. And the second thing is the full setting of Conan achieves the lowest WR, you see here, which means that, okay, the stream content encoder, extractor is useful. It preserves the content well. So lastly, the latency, we achieve about 37 milliseconds end-to-end latency under the fast setting. So, and also we have the real-time factors recorded here. The real-time factors, if they're lower than one, it means that we meet the real-time requirement. So apparently we meet the real-time requirement. So it's good. Okay, time for some demos. We have our source speech LibreTDS from LibreTDS dataset, and the transcript is printed as the text. And we have a reference speech from VCTK. The speaker is on scene, and you can hear the performance of the Conan full model and the Conan fast model.
He shrugged his shoulders in ungracious acquiescence, while our visitor in hurried words and with much excitable gesticulation poured forth his story.
Please call Stella. Ask her to bring these things with her from the store. 6 spoons of fresh snow peas, 5 thick slabs of blue cheese, and maybe a snack for her brother Bob.
Let's hear about the Conan performance.
He shrugged his shoulders in ungracious acquiescence, while our visitor in hurried words and with much excitable gesticulation poured forth his story.
And the fast version of Conan.
He shrugged his shoulders in ungracious acquiescence, while our visitor in hurried words and with much excitable gesticulation poured forth his story.
So we can hear that, okay, the content is preserved well, and also the speaker is similar to the reference speech. Yeah, so that's all of our work. We introduced Conan, a chunkwise streaming voice conversion system which A, preserves the linguistic content of a source utterance, and B, adopts the speaker information of a reference utterance. We have seen experimental results. Conan has great performance while meeting real-time latency constraints. Of course, we have future work. First one is how to rigorously explore the speaker style embedding because we don't actually have a metric to measure like the time varying prosody or information of the speaker information. And the second one is to enhance the model's generalizability, whether by increasing the data we're used to train and increase the complexity of the model to get a better performance, especially in out of distribution speech data. Yeah, so that's everything. And I've attached the QR code for paper, demo page, and code. Check out our paper and poster if you're interested. Thank you very much.